Most system design discussions look like this: load balancers, caches, queues, microservices, boxes and arrows everywhere. But real system design is not about diagrams, it is about maths. And if you ignore that math, your system collapses the moment real traffic arrives. When engineers discuss system design, the conversation usually sounds like this. We'll put a load balancer in front, add a cache here, maybe introduce a messaging queue, split services into microservices, and suddenly the whiteboard fills with architecture diagram. But those diagrams are actually solving something much simpler. They are trying to control the time and data movement, more specifically latency, throughput, bandwidth, and request volume. At its core, system design tries to solve one fundamental problem: how do we move data closer to CPU and serve it faster without overwhelming the processor or the network? Modern CPUs are incredibly fast, but the rest of the system, memory, disks, networks, is much slower. Every time the CPU waits for data, performance drops. And when millions of users hit your system, those tiny delays turn into massive bottlenecks. Different storage layers have drastically different access times. Accessing RAM instead of L1 cache can be 100 times slower. Accessing disk can be hundreds of thousands of times slower. And a network request is even slower. This is exactly why we design systems with caching layers, CDNs, in-memory databases, edge servers. Because the closer the data is to the CPU, the faster the system becomes. Now let's talk about traffic. Imagine your app has 1 million users. Each user sends one request every minute. To calculate how many requests your system receives per second, we use this formula. Here is how it works. If 1 million users send one request every minute, that means 1 million requests are spread across 60 seconds. So we divide 1 million by 60, and that gives us roughly 16,000 requests per second. That is how much traffic your backend system must handle continuously. There is another formula engineers quietly use when designing systems. It is called Little's Law. It looks simple, but it is incredibly powerful. Here is what it means. L is the number of requests currently in your system. Lambda is the arrival rate, basically your requests per second. W is the average time request spends in the system. So if your system receives 16,000 requests per second and each request takes 200 milliseconds to finish, then at any moment your system is handling roughly 3200 concurrent requests. This single equation tells engineer how much capacity their system actually needs. We also need to think about bandwidth. Bandwidth is simply how much data is moving through your system every second. We can estimate it with a simple formula. Bandwidth equals request per second multiply the size of each response. For example, if your system handles 16,000 requests per second and each response is 100 kilobytes, your server must send about 1.6 gigabytes of data every second. It is network bandwidth. The next time someone draws a system design diagram, remember, behind every box, behind every arrow, there is a simple truth. System design is just math, and the engineer who understand that math are the ones who build systems that actually scale.